Now that we've been working with matrices sum to solve systems of equations, let's turn our attention to focusing more on the arithmetic that we can do with matrices. We've seen we can use them and convert them to reduced row echelon form or just row echelon form to solve these systems that we've been talking about. But now let's look into the theory of the matrices themselves a little bit. So just to catch us up, right, let's remember that when we say we have an n or an m by n matrix, here what we're looking at is an array of numbers where there are m columns and n rows. So we've been calling these A, and then we'll have like A11 in the first entry, and there are m rows in columns. Right, so we have A11 through A1n, because there are n columns, and then there are m rows, so AM1 through AMn. Sorry for that, it's always rows by columns, right? And we know if m equals n, this is called a square matrix. Square matrices will play a really important role in some of the topics we'll study in the future. So if we had a square, right, then you would just say like A11 along the diagonal, you would have A22 all the way down to ANN, A1n, AN1, right? And you could fill this in. Instead of writing this out every time, I'm going to introduce some new notation here. Well, if we have that I is the index for m, or the number of rows, and then j is the index for the number of columns, so j runs from 1 to n, then I'm going to introduce the notation that this matrix A is compactly written as A sub ij, right? This will be one way we can talk about just the entries of this matrix, right? Okay, we've talked about a square matrix. We have the zero matrix. The zero matrix is going to be, cleverly enough, it's going to be a matrix of all zeros. And we'll just write this as 0. So like, of any size, right? I haven't specified a size here, but every entry is a 0. So if you had the zero matrix for a 2 by 2, this would be just 4 zeros, right? Like et cetera, for different sizes. Now, to address the different sizes of the zero matrix here, the zero matrix of any two different sizes is not the same matrix. Even though all their entries are 0, they're not the same. So we want to talk about what does it mean for two matrices to be equivalent. So let's look at equivalent matrices. For two matrices to be equivalent, you need to have that A and B have the same number of rows and columns. And then we also need that every entry Aij is equal to every entry Bij here. So again, this is where when we were calling this A, the matrix Aij, and then similarly B, we can write B, this is the matrix Bi. J. So for two matrices to be equivalent, they have to have the same number of rows and columns, and every entry needs to be identical. So for example, here, the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, and the matrix 1, 2, 3, 4, 5, 6, 7, 8, 8. These matrices are not the same matrix, right? It's pretty obvious when you have two different entries, like, well, of course, that's not the same. But you do need every single entry to be identical. Also, you have to have the same size of matrix on each side. So for example, with the 0 matrices here, so let's have a 2 by 2 0 matrix, and then let's have a 3 by 3. These are also not equivalent, right? Those are different matrices because they have different dimensions, right? The number of rows and the number of columns are different. Okay, so now what about adding two matrices? Let's look at matrix addition. Here, if we have a matrix A, which will be given by A sub ij, and B, another matrix given by B sub ij, and let's let these two matrices have the same number of rows and columns. So let's say these are both M by N matrices. Well, then the sum of matrix A plus matrix B is defined component-wise or entry-wise, right? So C, we will define this to be A plus B. And if we call C C sub ij, then each entry of the matrix C is given by A sub ij plus B sub ij, right? So really you just take each entry from A and add it to the same entry from B, and then the sum is pretty pretty straightforward there. Then you just take the sum of the two numbers from those entries, right? So if we had an example, and I want to emphasize quickly before the example, these are necessarily the same size, right? A and B have the same size. Matrix addition is not defined if the matrices being summed together are of different sizes. So always make sure that when you're adding two matrices, they have the same size or the same number of rows and columns. So let's do a quick example here. Let's look at two 2 by 3 matrices. So we have the 2 by 3 matrix A, which will be 1, 2, 3, 1, 0, 4. And then we have B. This will be the next matrix, 5, 2, 3, and then negative 6, 2, 1. Well, if we define C to be A plus B, then this is going to be 1, 2, 3, 1, 0, 4 plus 5, 2, 3, negative 6, 2, 1. And this would simply be, well, we add component wise, and I'll do this in a little more detail for the first time. But in general, once you get the hang of it, you can really omit this next step here. So we would have like 1 plus 5 for the first entry, and then 2. So like for the 1, 1 entry, we would have 1 plus 5. For the 1, 2 entry, we would have 2 plus 2. For the 1, 3 entry, we would have 3 plus 3, right? For the 2, 1 entry, we would have 1 plus negative 6. For the 2, 2 entry, we would have 0 plus 2. For the 2, 3 entry, we would have 4 plus 1. And you can see this would give us 6, 4, 6. And then it's like negative 5, 2, 5, right? So this would be the sum of matrix A plus matrix B. And you can see the resulting matrix is the same size as well. These are 2 by 3. And so is the result. And that's important. Okay. We know how to add two matrices. Now let's see some properties of matrix addition. Okay, we have that matrix addition is commutative. Excuse me. We have that matrix addition is commutative, meaning if you have two matrices A and B, A plus B, well, this is necessarily the same as B plus A, right? That's what the commutative property gives us. We also have the associative property. We have, if you take A plus B plus C, this is the same as A plus B first, and then plus C, right? So we can see the order of the sum can be changed. Now let's look at not so much properties, but more of kind of like rules or things that these that matrix addition satisfies. So it satisfies that it has an identity, namely the zero matrix, right? Because if you take, what's an identity, right? An identity is something that when you apply the identity, or when you apply this operation to a matrix, you get the same matrix back, right? The matrix A, after you apply this operation, you get the same matrix back, right? In multiplication, the identity element is always 1, right? Because if you take something times 1, you're going to get itself. But for addition, the identity element is 0 because you have something plus 0 is itself. So we have the identity here, which is the 0 matrix. And we also have an inverse. So let's say it has inverse. And we'll write the inverse as negative A, right? Because what's the inverse element? An inverse element is when you apply the operation to a matrix and then you get 0, right? And so, or you get the identity. And so we want to apply something to A such that we get 0. Well, that would just be negative A. And by negative A, we mean that we're just taking the matrix A and then scaling every entry by -1, right? So if you had A is the matrix Aij, well then negative A would be the matrix negative Aij. So that negative just goes to every component, right? And you can see if you sum those two matrices up, you would get the 0 matrix, which is the identity. Okay. So next we can talk about scalar multiplication. With a matrix. So let's again say we have this matrix A, which is given by Aij. And then let's take some real number, or K, to be a scalar. Then we can define a scalar multiple of a matrix as you just multiply every entry of your matrix by this number K, which is really here, this negative A. This was just for K equals -1, right? This was scalar multiplication of the matrix A for K equals -1. So let's look at an example of this here. I guess I'm still in red. What we could do is, let's just say K equals 2, and then we can use A, we'll make it a 3 by 3 matrix. 2, 1, 0, 5, 7, 1, 3, 4, 2. Well, then what is Ka? Well, in this case, it's 2A, right? And so what is the matrix 2A? Well, this is really just, and again, you can omit this step just so it's very clear what we're doing. Well, this would be 2 times 2, 2 times 1, 2 times 0, right? Every entry I'm just multiplying by 2. 2 times 5, 2 times 7, 2 times 1, 2 times 3, 2 times 4, and then lastly 2 times 2. And so you can see the matrix, the resulting matrix with the scalar multiple of 2 here would be 4, 2, 0, 10, 14, 2, 6, 8, 4, right? And so we have this, this notion of scalar multiplication. This makes sense if you think about what we did with scaling vectors, right? Vectors are just, well, if it's a column vector, then it's going to be like an m by 1 matrix, right? This is also known as a vector. Well, we scale vectors all the time, right? We did this all the time in Calc 3, and now we're just looking at that for things more complicated than vectors, right? Just for matrices in general. And that's what we have here. And I'll quickly go over the properties, some properties of scalar multiplication. We have the distributive property. Meaning if you have a scalar k, and then you're applying this to a sum of 2 matrices, well, then this is the same as Ka plus Kb, right? And so the scalar distributes across the matrix addition. We have, so let me be more explicit here. We have distributive over matrix addition. And then we also have distributive but over scalar addition. So let's say we have 2 scalars here. Let's say we have K and L, and we're adding 2 scalars, A and L, or K and L, rather, and we are multiplying this, or we're scaling the matrix A by this K plus L. Well, then the scalar multiplication distributes over scalar addition as well. So this would be Ka plus La. We also have associativity. And this is for scalar multiplication. For scalar multiplication. And this would be to say, like, well, if we have K, if we're scalar multiplying some already scaled matrix A, so say we have LA, and then we're trying to scale that by K, well, this is the same as first taking the product KL and then scaling A by the product KL. And then lastly, we have the existence of multiplication by 1, right? So really this is not so much a property, but at the bottom there's more of a rule here, is that we have multiplication by 1, which means that 1 times A just equals A, right? Okay. Now, well, actually, I think what I'm going to do here is I'm going to stop this video for now, and then the next video will be purely dedicated to the multiplication of 2 matrices. So here you can see we have this notion of adding matrices, and then when we went to multiplication here, well, we're not multiplying 2 matrices together. We're multiplying a real number by a matrix, right? But we want to be able to multiply 2 matrices together. And so in the next video, we will completely explore the topic, or at least introduce the topic of matrix multiplication.